Well, I now show you some specimen calculation for burst strength. Let us say that tire inflation pressure, that is P of T is equal to P of G is equal to 650 kilopascal. And maximum size of stone is equal to 60 millimeter. Then cumulative reduction factor is equal to 1.5 and factor of safety, let us say 2.0. So, you know the equation, factor of safety is equal to 60.6 into P of B, this divided by P of G into D of A. So, PB is equal to F of S P of G into D of A, this divided by 60.6. So, this will be equal to, because factor of safety is 2, this factor of safety is equal to 2, this is 2 into P of G, Pg is 650 into D of A. D of A is maximum size stone 60 millimeter. So, this is 60. This divided by 60.6. So, this will give you that 1287 kilopascal. So, the required burst resistance is 1287 kilopascal. So, this also you can determine from this figure. You can see here that pressure geotextile stone aggregate, in the problem it is given 650 kilopascal, this is 650 kilopascal, and stone diameter is 60 millimeter. You can see, considering this as a stone diameter 60 millimeter. So, knowing the pressure on the geotextile 650, stone diameter 60, so you can determine what should be the required burst resistance. So, the required burst resistance is about 1287. So, this is required burst resistance 1.827 kilopascal. So, from this design chart for burst analysis of geotextile, we can make use of this design chart for the determination of required burst strength of geotextile material. I am giving another example. You know that, let us say, factor of safety is equal to 60.6 into P, this divided by, let us say that stone on the geotextile, let us say this is P dash into D of A. So, you know that dB has a relationship with the D of A. So, I am telling about what is dB, I will explain this one later on, that is maximum void diameter of the stone. This will be equal to 0.33 D of A, where D of A is the average stone diameter. Average stone diameter. And this P dash, you can stress on the geotextile. P dash is stress on the geotextile, which is slightly less than P, that is star infiltration pressure. Inflation pressure on the ground surface. I will explain later about the maximum void diameter of the stone is equal to 0.3 times of D of A. Okay. dA is equal to average stone diameter. So, let us give another example. That given track, that pressure is 700 kilo Pascal. This 700 kilo Pascal. Now, this is, let us say here about P dash is equal to 700 kilopascal, and this is rest that track tar impression paper of poorly graded aggregate layer and consisting 50 millimeter maximum size of the stone. So, stone size is 50 millimeter. Okay. So, that means dA is 50 millimeter. And you have to determine what is the factor of safety using the geotextile beneath the aggregate having the ultimate brush strength. Ultimate brush strength is given. Brush strength is 2000 kilo Pascal. Okay. And cumulative reduction factor is given. Cumulative reduction factor, this is equal to 1.5. So, you have to calculate that factor of safety. So, factor of safety, you know, 60.6 into ultimate brush strength value okay, that is 2000. This divided by, you know, P dash value is given 700 into that diameter dA. dA is equal to average stone diameter, that means this is 50. So, if you calculate, you can find this factor of safety will be 3.5. So, the reduction factor 1.5 is already included. So, resulting factor of safety is acceptable. So, this is acceptable. Okay. So, this factor of safety is acceptable. Now, I will discuss the graph tensile test. So, graph tensile test is performed as per ASTM D1682. The main objective of this test to determine the graph tensile strength of geosynthetic material. And introduction, the test rely on filament interaction in geotextile. For non-woven geotextile material, the effects are more than the woven geotextile material. And graph strength is required to design the geotextile for separation. You know what is the separation? Now, when the pressure is applied on the upper surface of the stone, for an example, and how it spread on the lower surface of the stone. Let us say this is one layer of the geotextile material. So, this is geotextile material, okay. And these are the subgrade. These are subgrade. And these are the stone, these are also a stone. And this diameter of the stone, let us say this is d by 2 and this distance is d, this distance is d, and the top of this there is another stone material and whose diameter let us say d, and this is the pressure is acting on this, that is designated at P. So, these are the stone. So, this I am showing that fill model, this is fill model for graph tensile strength. This is the initial condition. Initial condition. So, when the pressure is applied to the upper stone and it's spread the two lower stone laterally. As a result, there is a tension is mobilized in this geotextile. It is analog to the graph tensile strength test. Now, how it can be analyzed in the graph tensile strength material? So, if this is the geotextile material, this is geotextile, and after applying the load and this is D, this portion is D by 2 and this portion is D by 2. So, this is the stone and this is geotextile material and this is subgrade. So, when you load applied in the initial stage and then there will be a lateral in plane deformation, lateral in plane deformation after application of load on upper stone. So, after application the load on the upper stone, as you have seen earlier, then this will be the position. So, this is the final position. So, final position will be this to this. So, this distance will be equal to, let us say, L of F. Okay. So, this can be analog to the graph strength test. So, how it can be analog to the graph strength test? So, this is the, let us say, this is the sample of geotextile material and you have to perform the test. So, this is moving along this direction. So, this you can say analog gas graph tensile test. This is the lab model. So, you have seen that what is that a field model and how you can show it in the laboratory model. Now, from this, let us say that D is the diameter of stone. Okay. D is the diameter of stone. So, initial length of geotextile is equal to D by 2 plus D by 2 plus D by 2. So, if you can look here that initial length D by 2 and this is D by 2 and this is D by 2. So, that means 3 D by 2. and after applying load, that final length of geotextile will be equal to d plus 2 to d by 2. So, if you can see that after that final that when you apply the load, so this is d by 2, this is d by 2 and this is d. So, d plus d by 2 d by 2. So, that is why 2 d by 2. So, without any stress breakage, or slippage, the maximum strain in geotextile can be expressed as that maximum strain will be epsilon is equal to final length minus initial length, this divided by the initial length. So, final length that is here, that is d plus 2 d by 2. So, this is the final length d to d by 2. This minus the initial length was Li is equal to d by 2 d by 2 d by 2. So, you can write initial length is d by 2 plus d by 2 plus d by 2, and this divided by the initial length, means you can write 3 of d by 2. So, if you calculate, you can have 1/3, and that is equal to 33%. Okay, that is why this epsilon strain value is 33%. Now, from this you can determine what will be the tensile strain T required of the geotextile material. So, T required will be equal to A of P into dV square into epsilon. So, this is given by Giroud in 1984. So, where T required is equal to required graph strength and A of P, this AP is applied pressure, AP is applied pressure, and this is D of B, this dV, maximum void diameter. So, this is maximum void diameter, So, this will be equal to 0.3 3 times of d of A, where d of A is equal to average stone diameter. This is average stone diameter. dA is equal to average stone diameter. So, you can, knowing the value of the applied pressure and the maximum void of the diameter or the average diameter of the stone and the strain. So, you can determine that what will be the required graft strength of the geotextile material. Now, so what kind of the equipment or accessory required to perform the graft tensile strength? If require the tensile testing machine and you require the clamp. You can see here, this is the tensile testing machine and this is the clamp and this is the geotextile material. And this geotextile material is before the test and this is the graft tensile test after the test. So, initially this is geotextile and this geotextile is grabbed with this. So, it has a certain dimension, that is, this will be about 50 millimeter and from here to here about 75 millimeter, and the sample size is 100 millimeter into 200 millimeter into 200 millimeter. So, this is the graft tensile test apparatus. So, the procedure for this graft tensile test is that you have to mount the specimen centrally in the camp and start the tensile testing machine. The tensile strength is directly measured from instrument as maximum force per unit width to cause the rupture. So, graft tensile stress is reported as kilonewton, not as a kilonewton per meter. As the sample is partially clamped, the stress is not propagated in the entire width of the sample. So, it is unusual test and widely misused. So, I am giving one of the example for this test. So, you know that what will be the required graft strength equation? T required is equal to P dash into dB square into epsilon, or this is AP. We have considered AP into dB square into epsilon. Here you know dB means 0.33 times dA. So, this into 0.33 dA, this whole square into epsilon. So, let us say a given torque of 700 kilopascal torque implementation pressure, okay, on the stone base crust and 50 millimeter diameter of the stone. So, size is 50 millimeter. So, you have to calculate the what will be the required graft tensile strength of the geotextile material and what will be the factor of safety whose maximum graft strength suppose is given 500 Newton with a cumulative reduction factor is equal to 2.5 and strain value is given, let us say 0.52. So, T required you can determine, you know the what is epsilon is 0.52. So, and P also is known to you. So, if you can calculate, then you can have this equation. This will be like this 0.057 into AP into d square. So, this will be 0.057, this into AP is 700 infiltration pressure into 1000 into 0.050 square. Okay. This is dA. dA is 50 millimeter size, because dA we have considered 50 millimeter. So, this will be this. So, T required will be equal to 100 Newton. And factor for the 500 Newton Graf's tensile strength, when it is given, that 500 Newton Graf's tensile strength is given, and factor is given is 2.5. This is here what I mentioned in second case. So, you can determine what will be the factor of safety, that means this is T allow, this divided by what is T required. So, T allow will be equal to 500 divided by 2.5, 500 is this and 2.5. So, this will be allowed, and T required is the 100, which is determined. So, 100. So, this will give you the value of 2.G, which is acceptable. Thank you.